Hi, my name is Krish Sood, and I'm a sophomore at Winston Churchill High School. My project investigates whether a low-cost surface EMG system, combined with machine learning, can detect typing-related muscle strain associated with carpal tunnel syndrome risk. So, what is carpal tunnel syndrome? Well, it is a compression of the median nerve. When the wrist is repetitively strained, especially at awkward typing angles or positions, it causes the wrist flexor tendons and finger flexor tendons to inflame. When the tendons swell up, it causes increased pressure inside of the confined space of the carpal tunnel, and the median nerve compresses. Some symptoms of CTS are numbness, pain, weakness, and even permanent nerve damage. However, there are many gaps in current-day CTS-related EMG technologies. First, clinical EMGs cost thousands and thousands of dollars, making it hard for a doctor to have in their office. Second, patients today are typically diagnosed only after symptoms become severe, so there is no continuous preventative monitoring available in the market. Third, these technologies are invasive, meaning that they usually require a needle to be inserted into the patient's arm, which can then lead to even discomfort or even infection. And finally, these technologies are required to be operated by an expert technician or a trained medical professional. However, low-cost EMGs are scalable, they are affordable, and they can track your muscle activation throughout your daily life, even when you're working, playing games, or studying. The central research question to this project says that, can a low-cost surface EMG sensor combined with machine learning reliably classify muscle strain across different typing wrist postures? I came up with two hypotheses to answer this question. Hypothesis 1 says that non-neutral wrist angles while typing, such as a constricted position or an elevated position, will produce a higher muscle activation compared to a neutral baseline. Hypothesis 2 says that a machine learning model trained on EMG features can predict the typing posture at well above the 33% chance level that the model has to guess one of the typing postures. The figure on the left shows the surface EMG electrode placement on the forearm. Two electrodes were placed on the flexor digitorum superficialis and flexor carpi radialis, with the reference electrode being placed on the elbow. These three electrodes, combined with the MyWare 2.0 and Arduino Uno, were able to filter and digitize the participant signal while typing. Meanwhile, the figure on the right shows the three different typing postures the participant typed in. The first typing posture was neutral, at an angle of 0 degrees. The second typing posture was the elevated position, at an angle of 30 degrees above the horizontal. And last, the participants typed in a constricted position, at an angle of 30 degrees below the horizontal. The participants also completed a resting baseline trial and a maximum voluntary clench trial for preprocessing and normalization. This figure shows an example of a participant typing in an elevated typing posture. The bursts of activation show muscle contractions from keystrokes, but as you can see, the signal is very noisy, bipolar, and is not comparable across participants with our preprocessing and normalization. To get the data ready for machine learning analysis, I performed a three-step processing pipeline. First, I subtracted the baseline from the signal, which made the signal centered around 0 and removed most of the background noise. Second, I performed a full wave rectification on the signal, which took the absolute value of each data point. This was done because the sign of the signal does not matter as much as its magnitude, so it allows the magnitude to be measured more consistently. Finally, the third step was windowing, where the 60-second signal was segmented into 250 millisecond windows with 50% overlap, which means a new window started 125 milliseconds after the previous one. This allowed for stable features to be computed, while also keeping track of the fast dynamics of typing. Next, I extracted 5 features from each window: root mean squared, mean absolute value, waveform length, zero crossing rate, and slope sign changes. Root mean squared and mean absolute value were the most important features, as they measured overall activation intensity and average activation level, which give a holistic picture of how the muscle was performing during that typing period. Next, each feature was divided by the maximum voluntary clench reference to normalize the data. Because of the normalization, features represented a fraction of each individual's muscle peak capacity, enabling comparison across different types of participants. For classification, I used two machine learning models, one being logistic regression, which served as a simple linear baseline, and the other being random forest, which uses decision trees and captures nonlinear and noisy inputs better. To validate these two models, I used two strategies, one being within participant validation, which tests whether the system can learn an individual's EMG signature when it is calibrated to that person, and the other being leave one participant out validation, where you train the model on 10 participants and test it on the 11th, so the model can generalize to a brand new user it has never seen. This figure shows the within versus cross participant accuracy for both logistic regression and random forest. Logistic regression achieved 77.5% accuracy, and random forest achieved 84.6% accuracy under within participant validation. This was substantially above the 33.3 chance level for 3-class classification, which I said in hypothesis 2. However, under low-pool validation, the accuracy dropped to 49.4% for logistic regression and 52.8% for random forest. While still above the chance level, this drop was significant. It showed that while the system was inexpensive, the drop came because of the EMG signatures are highly personalized between users. The figure on the left shows the RMS distribution by wrist posture. The trend supports hypothesis 1, as the neutral baseline in the graph had the lowest value of 0.34, the elevated position had the second highest value of 0.37, and the constricted position had the highest value of 0.41, which means the constricted position had the highest muscle activation. A Friedman test was also performed on this data, and it showed that the data was statistically significant, as it had a p-value of less than 0.001. The figure on the right shows the mean normalized RMS per participant per posture. Once again, the constricted and elevated positions had the highest RMS values compared to neutral position, but it also showed a lot of variability between participants, suggesting why the cross-participant validation struggled under the machine learning models. There are a couple of limitations to this project. First, the project had a small sample size of 11 participants. Second, only 2 sessions were conducted per participant, so long-term signal stability was not investigated. Third, carpal tunnel syndrome directly was not tested here. And fourth, participants typed under specific conditions, but real-world typing is more fluid and variable. However, the system achieved a very high accuracy under within-person validation, suggesting there's more work to be done with this project. To conclude, a low-cost EMG system was able to detect and classify muscle-related strain at a very high accuracy using consumer-grade hardware. Some key takeaways were that a $45 sensor was able to classify typing postures at 84.6% accuracy when calibrated to one user. However, that dropped by 32 percentage points when generalizing to unseen users, evidencing strong individual variability in EMG signals. And finally, random forest was the better classifier for EMG signals because it was able to model the nonlinear relationship between the features and the wrist posture. For future work, I plan on creating a wearable prototype that works as a wristband and has a micro SD, battery, and secure electrode placement. I also plan on doing multi-day data collection with increased number of trials, longer sessions, different typing positions, and different typing speeds. And finally, I want to add a real-time feedback to my system, where I make sure that the device vibrates, beeps, or shows an app alert when non-neutral or risky posture is detected.